This video lesson will detail how to write and calculate using the equilibrium constant. So up until now in our study of equilibrium, we've used homogeneous equilibria as examples. A homogeneous equilibrium are reactions in which there's only one state of matter. So for example, this reaction, which we've seen, those brown tubes of gas we've used in class, um, are two gases in equilibrium. Here's another example. The ionization of a weak acid is all in the aqueous phase. But there are plenty of chemical reactions in nature that have other phases of matter, multiple phases of matter in the reaction. For example, this is the decomposition of chalk, which we've talked about before. We can symbolize by heating it up by adding a delta H there. But calcium carbonate chalk will decompose to calcium oxide and CO2 gas. So notice there's multiple phases of matter in the reaction. This presents some calculation trickery that we have to learn. In particular, the concentrations of solid or liquid phases are constant. So that's a little bit of a trick. You need to think about why. Solids have a number of moles per liter, and it doesn't matter how many liters you have. You'll multiply by if you have double the number of liters, you'll have double the number of moles. And so the concentration never changes. Same with a liquid. So they are constant and they don't affect the value of K. Whereas reactions like these two up here, in the gas phase or in the aqueous phase, concentrations can be variable. And so in different kinds of, different numbers, values of moles per liter, depending on how much reactant or product is present. So because solid and liquid values are constant, we don't use them in the calculation. We just kind of actively ignore them. So when we write K expressions, remember product over reactant of reactants with coefficients as exponents, we just ignore pure solids and liquids because it's a constant value. It doesn't change the position of equilibrium. The numbers are always the same. They're constant for solids and liquids. All you care about when writing the equilibrium constant are aqueous phase or gas phase because those values can be variable. So let me show you what I mean. Let's do a thought experiment here. Here is just some salt. Look at this chemical reaction down here. Look at some salt dissolving in water and ionizing. And that can be in an equilibrium state if you've got a little pile of salt. So that's what's shown with the red dots right here, pile of salt, and it's ionizing into sodium and chloride ions, but also turning back to a solid. So notice this reaction can go both ways. Also notice that because of the way salt ionizes, the concentration of sodium ion is equal to the concentration of chloride ion. So this is a saturated situation. We can't dissolve any more of that salt, no matter how much we stir it up. It's saturated. You can't again dissolve any more. And so we could add a whole bunch more salt. So I'm just going to add a bunch more red dots and make this pile of salt look much, much bigger, okay, than it originally did. And notice that, yeah, I can add a lot more salt solid, but it doesn't affect these concentrations right here. We can't dissolve any more sodium or chloride ions into solution, even if we have more salt. So for that reason, we just ignore salt or ignore solids in the dissolution expression. And it kind of works the same way with pure liquid phases as well. So here's an example of how we would write equilibrium constants if there's multiple phases of matter present. So this is an example. Methanol liquid is produced by reacting carbon monoxide gas with hydrogen gas at equilibrium. So I wrote let me use a red pen here. I wrote the skeleton equation right there. It doesn't look like it's fully balanced. You don't, by the way, you don't know what methanol is. I would give you that formula for that molecule, but it's CH3OH. This doesn't look balanced to me. It looks like I'm going to need two hydrogens. That's four, and I think that's all I need to do here. So the equilibrium constant expression, then let's write that. Remember, KEQ is always products over reactants with coefficients as exponents. But notice this product is a liquid phase, okay? And so we're going to ignore it and in its place just write a 1. So it's 1 over the concentration of these two gases, carbon monoxide times hydrogen squared. And so that's how you write an equilibrium constant with multiple phases of matter. Let's do a second one right here. So magnesium oxide solid reacts with carbon dioxide gas. There's your multiple phases of matter to produce solid magnesium carbonate. So once again, equilibrium constant is products over reactants with coefficients as exponents. The products here is a solid, so I'm going to ignore that and write, well, 1, okay, just because that value doesn't change. And it's over another solid, and we 1 times this value. So that's a gas. So we're going to write the value of CO2. Is that it looks like it's balanced. Yeah, it is balanced. So let's simplify that. And that's just really the value of 1 over CO2. Okay, so the equilibrium constant, position of equilibrium in this chemical reaction only depends on how much carbon dioxide gas is present. And that's all. So just remember that trick. So now we're going to move into calculating using equilibrium constant. Now that you know that one trick about pure phases of matter, solids and liquids. So the first thing you always do is write a balanced chemical equation, right? And it's particularly important now to write down states of matter because we're going to be actively ignoring solids and liquids. So you need to know phases of matter. You need to be careful about that. The second thing is, of course, write the equilibrium constant expression. Products over reactants, coefficients as exponents. But now, right, we're ignoring solids or liquids, and then simply substitute the given concentrations into that equilibrium constant you just wrote, and plug and chug. Solve for what the value of the equilibrium constant is. We'll do an example of this in just a second. Okay, but just remember that rule. The concentration of pure solids or liquid phases are completely ignored and not included in the equilibrium constant expression. So here's an example. Nitrogen monoxide and hydrogen gases. Let me actually hide a little bit of this. Nitrogen monoxide and hydrogen gases react to form nitrogen gas and liquid water. So that is a hint. Liquid water is a pure phase. We're going to ignore that one. So here's the two tasks. Write the equilibrium constant expression, number 1. And number 2, calculate the value of the equilibrium constant. So there's the second question right there. All right, so you're given concentrations of all the things that are in the reaction. So let's look. Nitrogen monoxide and hydrogen gases react, so that has to be my reactants. And what do they form? Nitrogen gas and liquid water. So here's that balanced chemical, not balanced, sorry, here's that chemical expression, the skeleton equation. And let's see, we need to balance. It looks like we need 2 nitrogens. So I'm going to put a 2 here. Then we need 2 oxygens. And we need 2 hydrogens. And I believe that's now balanced. Okay. So then you write the equilibrium constant expression. We have to calculate the value of the equilibrium constant. We've got to write the expression first. So products over reactants with coefficients as exponents. But remember, we're going to ignore any pure phases of matter. Let me undo that so you can see that that's liquid water that's produced. So that's not going to be in our equilibrium constant expression. So here it is. Products over reactants with coefficients as exponents. The only thing without a coefficient is my nitrogen. And then I chunk in the numbers. Again, this is just an exercise in plug and chug. So notice I've taken these concentrations and substituted in. For example, the nitrogen oxide squared is going to be 0.0081 squared, as shown right there. And that's a little bit of calculation work, but once you're done, it'll spit out this answer for the value of the equilibrium constant, 4.8 times 10 to the 11. Now, what's the meaning of that? Remember the meaning of the equilibrium constant. It's just a ratio of products over reactants. And this is a really big number, right? This is 480 billion. So that means the ratio is 480 billion to 1 of products versus reactants. So this is a reaction right here that goes mostly in the forward direction, right? Mostly makes products and not a lot of reactants are still hanging around. All right, that's a good intro to calculating and writing equilibrium constants, and good luck on the follow-up questions.